Assalamu alaikum and good day, my dear students. In this tutorial we will discuss scalar product in space. It's chapter 19 from your textbook. It's on pages 345 till page 348. The objectives of this lesson are definition of a scalar product in space, properties of a scalar product, relative position of vectors in space, and analytic form of scalar product. Before we start discussing our objectives, I would like you to help me and Mr. Yang to solve our little problem. While Mr. Yang is flying his drone over a horizontal road and he knows the trajectory of the plane, can you help us find the angle that the plane is making with the horizontal road? Okay, away you go. Definition: the geometric form of the scalar or dot product between the two vectors u and v is given by norm u, norm v, cosine u v. If O is any point in the plane, then the dot product of u and v can be given by the dot product of OA vector and OB vector, where OA equals u and OB equals v. Hence you notice that the dot product of the two vectors is independent of the position of O. Application: calculate the dot product of the vectors u and v of respective norms 3 and 6 units, where the angle between them is pi over 3. Solution: it's a direct application of the formula u dot v equals norm u times norm v times the cosine of the angle between them. Plug in the values of norm u and norm v and the value of the angle, and by the aid of the calculator you can find that u dot v equals 9 units. Notice u dot v is nothing but a scalar. Properties: scalar or dot product is commutative, distributive, and a vector by itself is u squared. A scalar by u dot another scalar by a vector v equals a times b into u dot v. Example: calculate the dot product of the following vectors, where you are given norm u and norm v and the dot product between the two vectors. Sign of dot product. With the aid of GeoGebra, we will study the effect of the angle between two vectors u and v on their dot product. Notice, if the angle between the two vectors is acute, then the dot product is positive. If the angle between the two vectors is 90, that is to say the two vectors are orthogonal, and the dot product between the two vectors is 0. If the angle between the two vectors is obtuse, then the dot product becomes negative. If the angle between the two vectors is straight, 180 degrees, then the two vectors are of opposite senses and direction, where the formula of u dot v reduces to minus the norm of u times that of v. Now what about if the angle is 0? If the angle between the two vectors is 0, the vectors will have the same sense and same direction, and the formula will reduce to norm u times norm v. What will happen if we change norm of either of the vectors u or v? Would the sign of the dot product change? No, it will not be changed. What happens if one of the vectors' norm is 0? Yes, the dot product will be 0, but that doesn't mean that the vectors are orthogonal. So if the vectors are orthogonal, it is necessary for the dot product to be 0. But if the dot product is 0, it is not necessary for the vectors to be orthogonal. Dot product and orthogonal projection. Let H be the orthogonal projection of point C on the straight line holding vector u. Now we need to compare the dot product between the vectors u and v and dot product between u and AH, which is again the orthogonal projection of vector v on straight line holding vector u. See, they have the same value no matter what the angle between the two vectors u and v is. Hence, by conclusion, dot product between any two vectors is equal to the dot product between a vector and the orthogonal projection of the other one on the line holding this vector. Analytic form of dot product. If u and v are any two vectors in a direct orthonormal system of origin O and base ijk, then we can write the dot product of the two vectors u and v as the norm of any vector u, hence the distance between any 2 points A and B, and the cosine of the angle between any two vectors u and v. For more details, read page 347 and solve exercises 5, 6, 7, and 9 from your textbook on page 354. See you next time.